Hi roboticist, today we are going to be talking about a full point cloud library tutorial. So by the end of this tutorial you will be able to sense, analyze and extract critical details from any 3D environment from task like robotics pick and place application that is able to sense the environment using a camera. So today I will guide you through the essentials of this 3D environment sensing like voxel filtering to simplify our data without losing accuracy. Then I will guide you through a pass-through filters, that is some kind of crop an image but this time in 3D. Then we're gonna go inside a plane segmentation details that is very useful in industrial application that involves any shapes of plane like a belt conveyor or simply a table, and you will understand why it's gonna be very important. And after that we're going to talk about cylindrical extraction, so in such a way that we are going to identify a specific object like cans, a cube, whatever it is, or any cylindrical shape, and we are trying to fit that object inside a cylinder, and this it will be very useful to calculate the centroid of the cylinder that we are going to extract, because then we can get the position of the centroid and run industrial application like a pick and place, because we will know the position with respect of the link from which the 3D data is streaming to. Okay, so before to deep dive into the point cloud library tutorial, let's discuss a little bit about the environment setup. So as you can see here, I have created a world with models that spawn a universal robot 5 cobot robots, where as an end effector I'm gonna have a robotic gripper with width of 85, and then I have created just a table that is supposed to be a simulation of a belt conveyor, then a normal table, a pallet, a basement, and this is gonna be a kinetic camera that is able to sense a 3D environment. So here I've chosen this camera because it has the gazebo plugin that is able to stream points cloud libraries. Okay. So if you want to have more information about this particular project, check out the full masterclass for being a robotics software engineer. I put the link in the description down below. Okay. Then I have spawned this object here. So the purpose of this video is to, let's say, save point cloud data that this camera is sensing, and then try to let's say find the centroid of this object with the respect of the optical frame link. So why the optical frame link of this camera? Because from the gazebo plugin, that link is the reference for streaming the point cloud data. Okay, so if you want to have a deep dive, So I have created this universal robot gazebo. So this is a launch file. So I have spawned this launch file. So I have created that is referring also to the universal robot file description. If you go to URDF, you have the Chakro gripper camera. Then if you go to sensor and then to the gazebo, you're gonna see that in the gazebo plugin you need to look at the frame name. So name optical frame. This name is set up at let's say the mother chakra file that is gonna be here. So the link RGBD camera underscore optical frame is gonna be the link of reference for streaming point cloud data. Okay, so having said that, what I would suggest to do is we have everything, let's say, to play with point cloud library data. Okay, so what I would suggest you to do is to create inside your Katkin workspace a new package that you can call it 3D underscore computer vision, right? And the dependencies of this package, it will be point cloud conversion, point cloud ROS, ROS CPP, ROS PI, sensor messages, and standard messages. Okay, so and this is very important. So then make sure to download the point cloud library in your machine, and to do that just run on internet. So basically, if you go to this website, pointclouds.org downloads, you just need to type this on your terminal, and then another important thing is that you need to install the point cloud underscore viewer, but we are gonna see in a while. Okay, so what then you can do is to save into a PCD file what the camera is streaming at the moment. So I have already done this. So if you go to SRV, if you go to inputs, then I have set up this test PCD. So this is a file that contains all the points that describes that the 3D environment, and actually is exactly what the camera is publishing. Okay, so if we go to the header of this file, we can see that the camera is able to publish 480,000 data. Okay, and this is a collection of a lot of points that has all this data in 3D. So this is gonna be the X, Y, and Z with respect of the RGBD camera optical frame. So in order to sense this, we can add a transform here. Then we are only interesting in seeing what is gonna be our link of interest. It should be this one. There we go. RGBD camera frame. So it seems that this is the center of the camera. So this is the positive Z, this is the positive X, and this is the positive Y direction. And the points that you're gonna see these are all related to that reference origin frame. Okay, so let's see what is gonna be inside. To visualize this point cloud data, what we're gonna do is to use a point cloud viewer. Okay, so here open a new terminal. And go inside this folder and run PCL viewer. Then the name of the file. There we go. So this is the data that the camera is seeing, and you can see that there's gonna be a lot of points here. So actually the camera is sensing the data with the color, but the data that I have saved is already filtered without the color, because this is an information that in this tutorial we are not going to use. So basically this that seems to be a unique figure, in reality if you zoom in you can see the point here, and all these points is represented from these three coordinate x, y, z with respect of the link RGBD camera optical frame. So it depends on the how you have set up your Gazebo plugin. Okay, so as I told you, the purpose of this tutorial is to process the point cloud data in order to get the object position of this cuboid here. Okay, I will give you some methods that are the most important that allows you to isolate the object of interest regardless the position in your environment, as long of course that is sensed from the camera, and I will the object is to get the position of this object with respect of the camera link. Okay, so let's close this and let's start with a new file from scratch. So let's go inside this src file, and so these are file that I have created in the masterclass course where we are going to deep dive into the vision system, in particular for all the application that regards the industrial robotics. So if you are interested in ROS and in ros2. I will suggest to have a look in this master. I'm gonna put again the link in the description down below. The course is still under construction. That's why you can benefit of 75% of discount with the coupon code pre-selling 75. Okay, so now inside the src file, let's create a new file and let's call it YouTube PCL tutorial.c++. Okay, there we go. So let's give some structure to this. So the first things that you need to do is to put all the needed libraries here. So let's do it. And here we go. So we need ROS, IOStream, because we are going to print something in the terminal. You will see later. File system, math, and then all the important PCL method, point types, all the type of filters, all the segmentation, and the voxel grid. But you're gonna see everything in a while. So if we wanted to give some structure to this file, let's create the main section. So now here simply we are going to set up the input, the path where the test PCD file is in, and the path of the output folder, and then we are going to create another file. So let's do it. Okay, there we go. So this is the path of the input and the path of the output. Make sure that to set up the absolute path. And here and here. So we are getting the test PCD file that we have just seen, and we are gonna save all the filtered points after to have processed this data into a file that you're gonna call filteredpoints.pcd. Okay, so then let's create a class, and let's call it, I will say, or better, a class, since that is more easier. Just create a function, and let's call it process point cloud library data, and we are gonna pass here the input PCD and output PCD. There we go. Okay, so in this function, we are going to take the input PCD and process the data with some method available of the PCD, the PCL library. Okay, so first of all, we need to create object of type point cloud type. To do that, we are gonna use the point cloud library class. And then the type of this object that we are about to create is of type PCL, and then point X, Y, Z. Okay. So let's set up the pointer. Okay. Then we need to create a PCD reader object to read the PCD file. And then we're gonna use it. Cloud reader to read what? We are gonna read the input PCD, and we pass in the input PCD the value of in cloud. Okay, so here from now on, everything that was inside the input PCD is passed to the variable cloud. Okay, so from now on we will deal with the cloud variable that has of type PCL point XYZ. Okay. So then we are going to create the same, but for the cloud filter, because it's going to be the new cloud that we are about to process. So just copy and readapt this. So then the first thing that we are going to to process is the voxel filter. So first of all, allows me to create this variable. This is of type voxel grid. I have done already a video on that. I'm gonna put the link in the top right corner. Okay, so Voxel filter is a kind of downsampling the data. So since that we have a lot of points in our environment, we want to. So the voxel filter is some kind of clustering the data. So I'm taking a point and I'm taking the points that are close to that point, and I'm calculating some kind the average of the value in the free space, and so in such a way that at the end I'm gonna have less point to process, but maintaining all the information of our environment. But with the visualization of the cloud filter variables, you will understand better, I'm sure. Okay, so let's pass to the voxel filter. Let's set up the input cloud. Okay. And then this is the most important thing that you need to set up when you are dealing with the voxel filter is to set the leaf size. So let's give it a number high, and then let's play with this later. I'm gonna write you that this is a variable that you need to play. So why to play? Because the higher this life size is, more distance are these points. More distantiated are the points, and the small value you have here, you're gonna have a small distance between each point. So you need to find a compromise, right? Because if you set up this high, means that okay, if you can process the data, the processing of the data that comes afterwards is going to be very easy, because since that you don't have a lot of points, then if you need to make a lot of calculation and your environment is changing very quickly, then the time of the evaluation, or if you are working with artificial intelligence, the time of inference will be less. Okay, but if you are going to put it small, then is not so efficient, is useless, because it's like to come back to have a lot of points in the cloud. And I remember you that we start from 480,000 points, which is a huge number. Okay, so then what we're gonna do is to filter. So voxel filter, then we need to filter, and then we are passing the value of cloud filtered. Okay, so we are passing to the value cloud filtered the object voxel filter that has passed through this this method here, belonging to this class. Okay, so then if you want to visualize the cloud filter in a PCD file, so let's create a PCD writer. So object, so let's call it cloud writer. Okay, and then what we need to do, if before was read, guess what, now is gonna be write. So cloud reader dot write, then is gonna be the same type, so a PCL point x y z, then we are passing output PCD, then we are passing to the out PCD variable what cloud filtered, and then set this variable to false. Okay. Okay, there should be everything. So let's compile this file, because we are in ROS. So every time that you put a modification in a C++ code, you need to compile this, and you need also to create an executable file inside the CMake list. Let's do it and build the package and run this node. Sorry, I made this mistake. Okay, so the file has been compiled correctly. Sorry for this typo error. So let's go inside the output variable. Okay, and then we don't have nothing here apart the other file that I have created in the master class. So for the moment, just run the node. So ros run, the name of the package, okay, and then the executable file. There we go. So it's done. So here are gonna be the filtered points. So let's have a look here. So again, here you can see that we started from 480,000 points, and we got 20,180 points. Right, so but what is the aspect of this PCD file? Let's have a check, and let's use it. Point cloud viewer. Then filtered. There we go. Here you go. You can see here that we have less points. We have maintained the shape, so we didn't lose any information about our environment, but we have less point to process, right? So have a check here. So if we open another terminal, let's run in the output, in the input, sorry. Okay, you can see here that here the original value, the original file, you have a lot of points. Okay, so if we zoom out, it seems like one image. It's very flat, the surface here. Okay, so I hope that you get the point. Let's move forward. What we're gonna do now is the plane segmentation. So the plane segmentation is a very useful tool provided by Point Cloud that allows us to segmentate all the surface that can fit inside a plane. Okay, so for example, if you have a table, so if you have an object that stands on a table, so the information of the table is not useful, and if you have to sense the environment and detect the object position, then the information of the table, of course, is going to change the center of the object, because it gives data that are outside the object of interest. So we don't want to get. So we need to filter this information by scanning the all the points and check if in the surrounding area of a certain points we can fit a certain area inside a plane. Okay, so the most important thing in the plane segmentation, or in general object segmentation in point cloud, is that you need to have the indices and the coefficients. Okay, so first of all, what are the coefficients? So you need to know that. So first of all, let's create this, and then let's talk about later. There we go. So we have created a SAC segmentation of type point XYZ segmentation. Then we have created the indices and the coefficients, and then we set up the cloud plane. Okay. So what are the coefficients? Where in the 3D space, a geometrical shape can be represented by coefficients. So you need to know that if you wanted to describe a plane inside a 3D space, you need to have 4 coefficients. Okay, I don't want to go inside the detail of the algebra, but you need to know this. And the indices are the indices of this points cloud. So for example, this is the indices 29. Okay, so the method of geometrical segmentation, and here in particular plane segmentation, is able to scan all the points here and find the coefficient, the indices and the coefficient that can fit a certain geometrical shape. And in this case, we are going to use the plane. Okay. So here we need to modify the object seg in order to segment a plane. So first of all, we need to set optimized coefficients as a true. And then here we need to set up the method type and the model type. So the set method type is where you set the type of the geometrical shape that you want to segmentate, and in this case is gonna be a SAC model plane. Okay, and we need to set also the model type. So what is going to be the algorithm model that we are going to use to segmentate our points. And this is going to be PCL. We are going to use SAC run SAC. Okay, then you need to set up the maximum number of iteration. $100, and then seg set distance Okay, so the distance threshold says that how far we want to include the point from this plane segmentation, okay? But you're gonna see in a while visually, okay? So then we need to set the input cloud. So now we are gonna pass the cloud filtered, so the cloud that has been voxelized, let's say. Okay, and then we segment, and we need to pass through these segmentation activities the inliers plane, that is gonna be this one, and the coefficients plane. Okay, so now we need to extract the plane from the variable seg. Okay, so what we need to do? So we are gonna we want to set a negative plane. We are gonna see in a while. So we wanted to put it, and we are going to put it true, meaning that we want to have an image in 3D that subtract the plane. So let's see in a while what is gonna be. So we need to use extract indices. PCL point x, y, z. Okay. Then, as always, we need to set the input cloud, that is gonna be set input cloud, that is gonna be cloud filtered, as always. Okay, and then we need to set the indices. So neg plane e so this is the variable. This is important to set it true. You will see in a while why. And then finally we need to apply the filter method. There we go. So save, compile, and run, and let's see what's happened. Okay, there we go. You can see now that the new plane, or better, the new image has no plane anymore, because thanks to the plane segmentation, we have applied the model type SAC ransack and the SAC model plane to scan all the points, and we have found the coefficients and the indices of the point data that fits inside a plane. Okay, so we set it to set negative to true, meaning that we are going to subtract the plane that we have found in our environment. Okay, so what's happened if we set up as false? I think that you got my point. Let's build. Here we go. Since that now it's set negative to false, we have only the plane. So if you are interested in a plane, then you can use the set negative to false, and this is very useful. For example, if you need to run inside a robotic application where you need a dispense a glue inside a plane. Usually in industrial application you dispense the glue on the edge of a plane, and you need to sense right the plane. Then you can use a point cloud library, plane segmentation, and set the negative to false, and here you have your plane, and then you can get the coefficients of the plane. So in your inverse kinematics algorithm, you can say to the end effector of your robot to follow the direction perpendicularly of the plane that the camera is detecting. It's very powerful, this plane segmentation. Okay, let's move forward, and this let's put it to true. Okay. Now what we are going to deal with is the pass through filter. So this is very easy, okay, and this is gonna be like crop an image, a 2D image, okay. So if you are not interested in the information of an image, what you do, you crop, and that's it, okay. So the pass-through filter is exactly the same thing, so with the difference that it's gonna be in 3D, and you need to pass the interval in XYZ to which you want to get the data, okay. So let's see what I'm talking about. So first of all, let's start with the pass-through filter in Z, okay. So let me do it right away. There we go. So I have created a variable pass through pass. Then, as always, you need to set the input cloud. So the cloud, and in our particular case, is the cloud that has passed through all this method here. Then you need to set the filter field name Z, and remember that the Z is gonna be this column here. Okay, so you can see what is gonna be the value, and then set this accordingly. Okay, so I have tested this before. Let's build a package and run again. Okay, let's see what we get. Okay, so you can see that you have get out already a lot of data. So because I remember you that the camera is it's here, so the distance from the camera is the z coordinates. Then here is gonna be the positive x, and here is gonna be the positive y. Okay, but if you have any doubt, you can check. You are gonna check the RVs, the RVs transform model. Okay, so since that I'm losing a lot of data, what I would suggest you to do for the purpose of this tutorial is that let's say that I'm gonna get more points, so I try to get this distance between the points thinner. Here you can always select in different directions, so you can have a thinner leaf sides in the z direction. It depends on your model, on your 3D environment, but let's do it like this. Okay, then guess what, for the part cropping an image in the x y direction is gonna be easier, because you just need to copy here and here, then set up this could be the x, this is gonna be the y, and of course you need to find the good variable for this. So I have tested offline, and here I've seen that in order to isolate my object, I'm going to set up this at 0 and 0.2, and in y I'm going to set up minus 0.2, and 0. Okay, so let's build the package running again. And there you go. You can see now that we have already our object isolated, right? Because the pass-through filter, the segmentation, the voxelize, the segmentation, and the pass-through filter in all the direction makes our object to be very isolated, right? So this is a good achievement for the moment. Okay, what you can have, of course, here this is an environmental representation, but in real life you can have some outliers, right? And depending on how the noise of your environment, how noisy is your data, you might want to remove the outliers using a statistical outlier removal filter. So if you have already experienced in OpenCV and image recognition, usually you're gonna use some Gaussian filtering, right? So we're gonna detect a mean of a certain value, the standard deviation threshold, and we try to clean a little bit the object according the intensity of the data that we are getting in a certain point. Okay, so in such a way that all the queue is going to be removed, right? Of course, in this case, it's not so much important because the pass-through filter has done a pretty good job. But for the scope of this tutorial, I'm gonna tell you how to do that. So here we're gonna move to remove the outliers using a statistical outlier removal filter. Okay, let's do it. Okay, there we go. So this is nothing to say. So basically, this is the source. This is of type statistical outlier remover class. Then, as always, set the input cloud. You need to set the mean, the multi-threshold standard deviation, and then SOAR filter. Okay, I'm not testing here because you will see that you can do it, of course, but you can see that you will not do nothing. You will not obtain added value out for this because it's already isolated the object, right? Okay, now is come the most interesting thing, in my opinion, and we are going to segment a cylinder, using a ransack method. Okay, so basically, why cylindrical segmentation? Well, the concept is the same of the plane segmentation. The point to use a cylinder because in many industrial application you can have an object with a fancy shape, right? Above all, if you are gonna use, if you are working in consumer goods, for marketing purpose, you're gonna have a really crazy shape, okay? But you're not interested in sensing the craziness shape, right? You just want to have the centroid of this shape. So it's very important to try to fit your crazy shape object inside a geometrical cylindrical inside a geometrical shape where you know what are let's say the main component, the characteristic component of the object, right? So imagine that here we are going to have a cuboid, okay, and then where we can fit it into a cylinder, right? And a cylinder, we know that we can describe a cylinder inside a 3D space, but it needs to have a radius and a length, right? So if you are able to fit this object inside a cylinder, then we can calculate easily the centroid of this object, right? In such a way that somehow we are getting the centroid, and we are not picking the object from the side, for example. But of course, it depends on your application. Okay. So when we are talking about the cylinder and surface and a surface in general, another important concept is that the segmentation, the cylindrical segmentation works with normals. Okay, so if you have a shape of cylinder, you need to divide your cylinder in small points to which you're gonna have the normals that is pointing out from the surface, is radiant to the surface, and then this method uses these normals to calculate the cylindrical shape. Okay, so after this introduction, what we need to do is to get the normals, and what we need to do is to use the point cloud method. This is of type PCL, this time point normal. And then PT pointer, and then cloud normals. There we go. There we go. So we have instantiated the point normal variable. Then we need to estimate the normal. So we need to instantiate this normal estimator, and then we are gonna use the KD tree. So this is the method that we're gonna use to search along all these points the normals that can fit inside a cylinder, right? So here you're gonna set the search method that is gonna be this one to get the normal, and then you need, as always, to set the input cloud, set case search, meaning that this is a play variable because it's seems so it's from each point from which to which we can looking for a normals. Okay, so in such a way that if we are getting for example 50, means that we are evaluating 50 points to see if we can create some kind of normals. Okay, and then you need to use the normal estimation compute to the cloud normals that we have just created. Okay. So now what we need to do is to segment. We need to make a segmentation. the cylinder from the normal. So here we are trying to make a cylindrical segmentation, okay, from the normals. Okay, and this is very similar to the plane segmentation that we have seen. So let's see what is going to be. There we go. We need to use the sag segmentation from normals value because it's exactly what we are going to do. Then we have created this variable, and then we need to set the optimize coefficients, set the model type. This time we are going to use a sag model cylinder, and before we used the SAC model plane. Okay, we're still using SAC run SAC as the method type. Set normal distance weights this time. Then 0.1 maximum iteration, we are going to increase the iteration. Set the distance threshold 0.05. Radius limits is this one. So since that we have an object that has a square section of 20 millimeters, of course the radius limits is gonna be this one. So it's not important to be very precise, but you just need to give a range. Okay, then we need to as always set the input cloud filter, and then the set input normals. Okay, then what we need to do is, as always, if you wanted to run a segmentation, you need to get the inliers and the coefficients. So this time we need to get in, we have segmented our cylinder, right? But then we need to get the indices of the points and the coefficients that describes our cylinder in a 3D space, right? So let's get this. Okay, and then finally we can extract the cylinder. Okay, so we need to set input cloud, set indices, and set negative, this time false. Again, if we put true, then we are senses all the environment except of the cylinder that we have just extracted, right? So, and as last, we need to filter, so cylinder extracted, then filter, guess what, the cloud filtered. There we go. So since that we are here, we can compute the centroid of the extracted cylinder. So compute the centroid of the extracted there. Okay. So we can run just once, and then we get from the terminal the centroid of the object that we have detected. There we go. So I have created a vector for f, centroid. We need to compute a 3D centroid from the cloud filtered, okay, and pass it to centroid, and then we need to simply print on the terminal the value. Okay, let's compile and run. Okay, so here, for example, we can see that we are not seeing the object, right? A suggestion that I will do, I will give it to you, is to, for example, probably this is gonna be too tight. And then let's comment this out. Okay, and probably let's make it, I will say, more thin. So let's test it again. Okay, now we got a value that makes more sense. So the centroid of the object that the camera is detected, it have this coordinate. So is in x is 0, then minus 0.1 in y, and around about 1 meters in the z direction. So let's see what we have it here, and we can see here that we got the object, and I know that it's gonna be difficult to see, but you can slightly get the curvatures, but the most important thing here is that what you need to know is that we are sensing the environment correctly. So, but we're not interested in sensing here. We are interested in this data, right? Because this is really important, because then if we are gonna use, we are gonna get the position of a certain object with respect of a certain link, and in this case is gonna be the camera link. Then in ROS you might know that we can use the transform to get the information that we are getting from a certain frame to another frame. And usually when you deal with the robotics and inverse kinematics, you tell the end effector of your robot to reach a certain position with the respect of the base link. Okay, so if we apply to the transform this data here, and we transform this coordinate position in the coordinate with the respect of the base link, but well, we can tell to the robot to reach that position in order to pick and put somewhere else. Okay, so if we want to have a look of from we have started, so we have started from this environment, okay, as a recap. And then what we have done is to apply voxel filter, then plane segmentation, that we get rid of the plane. Then we applied a pass-through filter, this time in X, otherwise we crop too much. And then we apply a cylindrical segmentation, and we have fitted this object, even if it's gonna be a cuboid object, into a cylinder. And then we have extracted the centroid of this cylinder. Okay, that's all for today. I hope that you enjoyed this tutorial. If you want to master your career in industrial application, and you want to have a deep dive and become a real robotic software engineer with ROS and ROS2, let's check the link in the description down below. I will really suggest you to have a look on the curricula of the masterclass to become a real robotic software engineering for industrial application, for the project of your university, or very useful for the industrial application that your company is requesting. This gives you all the tools. We are gonna deal with ROS, move it, we are gonna run simulation, and we are gonna have a deep dive in the computer vision, like OpenCV and Point Cloud Library. And the scope of this masterclass is to give you all the tool that you need to have in order to deploy a robotics application from your own. So you will have all the instruments that you need to have, starting from the basic of ROS, creating a URDF file, then ROS control. We are going to create our model in Gaussian gazebo. Then we are going to use inverse kinematics, run the application in gazebo, OpenCV, point cloud library, and then we are run into a pick and place application and other industrial application like a palletizer, and so on and so forth. And a little disclaimer, this course is under construction, so you definitely not gonna pay the full price. There's gonna be a coupon, and I'm also working in the new modules that is gonna be ROS2 and how to migrate your project from ROS1 and ROS2, and this is gonna be very important. So at the end of this course you will have a deeper proficiency in ROS1 and in ROS2, and you can deploy any industrial application for your university or for the company that you are working with. Okay, so that's all for today. Make sure to subscribe to the channel if you like this kind of video, and thanks for your attention, and as always keep learning robotics with Ross.